So hello students. So today's class we'll continue the problem which we I think left halfway. So this was a problem which was solved midway. The case was eccentric loading condition with the load being an offset, and the cross section given was a T type, right? So in this problem you are required to find the stresses which is being encountered in both inner fiber and the outer fiber as seen in the figure, and also because of the load is being offset or sent into some other portion here, uh, that is nothing but the eccentric load, right? So somewhere over here this is the eccentric load. So we were analyzing this, right? So eccentric load, so but the centroid is here, somewhere here, so that centroid was not known. Since the centroid was not known, we were forced to find the centroid for where the moment of inertia is acting, right? So we solved for the centroid, and we came to know that it is at a distance of 55 mm. So x as 55 mm. So once we came to know about that, so we defined that is from the inner portion. So we consider this starting from the x point. So inner portion is 55, that is length of inner and outer. The next we define the governing equation, that is including this axial and bending moment both. Then we found the moment of inertia of the entire body. Moment of inertia of the entire body is found like this fashion, right? Once we have the moment of inertia about that particular point, that is x bar. I think we didn't solve this quite yet. Okay, so once you solve this yesterday. So you solve this and you'll get an answer like this. Select 13.67 into 10 power 6 mm power 4. So this is the moment of inertia of the entire cross section here. So this entire T cross section which you see, no? So this is the value for moment of inertia. Okay. Now let's find the total area. So why the total area? Because here you see A here. So A, whether it is for this or this, we just don't know. So let's find the total area before we go. So I is found out. So this moment of inertia I is found out. Then L naught is there. Li is there. That is the distance from the centroid to the inner and outer fiber. And we have the force here. We have the force. We have the bending moment also, I think. No, we don't have the bending moment yet. We need to find the bending moment, and we need to find the area. So let's do that. So area, the total area is nothing but the total area of the cross section is A1 plus A2. So area 1 here is the area of this portion here, that is 40 by 100, right? So this is equal to length 100 into 40 plus again area 2 is also 40 by 100. So it's both rectangles just placed in a different fashion. So once you multiply this is 4000 plus 4000, you get 8000 mm squared. So this is the total area, right? So now we have found the total area, and only thing left over is the bending moment, right? So bending moment, simple enough. So MB is nothing but the load F into eccentricity E, right? So eccentricity E is nothing but the distance. So this I think we found out yesterday. So you see here the eccentricity from where the force is being applied till the neutral fiber, where the neutral fiber lies. So this, if you see in the C clamp, the load is applied here and till here. So this dotted black dotted portion that is the total eccentricity. That means this is 150. That is distance till the inner fiber, and from there on it is 55 mm inside. So that's where you get this eccentricity is 205 mm. Right. So force we already know, that is 80 into 10 power 3. So 80 kilonewton was given, right? So check out the question. So 80 kilonewton is the force being applied into the eccentricity is 205. Right. So let's calculate this. 80 I'm getting 16.4 into 10 power 6 Newton mm. So this is the bending moment. So now in this these two formulae we have everything. Bending moment is also found. So we know everything in the RHS. Therefore, we can find the value for LHS, right? So let's just take this. So we are finding the inner stress in the inner fiber, okay, of the C clamp. Let's start off with that. You have force force 80 kilonewton divided by area we found 8,000 divided by 8,000 plus bending moment, we just found it out, 16.4 into 10 power 6 over moment of inertia I 13.67 into 10 power, what is that, 6, 10 power 6 into the length from the inner fiber Li comes from here, that is 55 mm into 55, right? So let's calculate this. Okay, so you calculate this, you get sigma I, the stress in inner fiber, as 75.99 Newton per mm square. Newton per mm square. So this is our one part of the answer, 75.99. Let's look at the second part now. There is a stress at the outer fiber. So stress at outer fiber is the same thing. Just what is the difference is, oh, the sign is not it's not minus, because you're applying a compressive load, right? I'll explain. This is minus. Okay, why? Because we check it out here. So this is not plus, this is minus. Why? Because you see, because of the applied load, this inner fiber will be subjected to tension, to be stretched, whereas outer will be subjected to compression because of the nature of how you're applying the load. Okay, so this is a tensile kind of load for inner, and for outer it is a compressive load. So that's how you need to evaluate this. So we'll be having the same thing. Only thing change will be the sign and also the inner fiber. So this is force, this is area minus and L naught. So L naught or LO, that is the outer length of the outer portion from the neutral axis. So this is our neutral axis, right? So from the neutral axis, it is 85 mm, the outer fiber. So we look at that 85. So this is into 85. So let's calculate this. 16.4 into 10 power 6 divided by 13.67 10 power 6 into 85, and you have 80 over 3 divided by 83 minus that answer. I'm sorry, small mistake. So this is 8,000, not 80,000. This is the same previous one. Area is 8,000, right? Not 80,000. Make a small correction. There's 8,000. Okay. Let's do that again. That divided by into 85 and 83. Right. So we are getting the answer. Just check with me. So this is equal to negative minus 91.98 Newton per mm square. Outer. So this is the outer stress. Stress experienced by the outer fiber. As you can see, as expected, this is negative. Negative meaning it is being compressed, right? And in here it is positive, where it means it is being stretched. So this is 8,000. Okay, make that small change. Right. So I think we have solved everything which is required. So determine normal stresses at the extreme fibers. So normal stress at extreme fibers, that is outer and inner fiber, we have determined using this case here. Right. We'll move on to next one. Any doubts is there? You can just post it in the group chat. Okay, let's try the next problem. Okay, so right, you can take a screenshot, or you can where you can note it down later on. So you need to determine the required thickness of the steel bracket at the section AA, and when load is shown in figure, in order to limit the tensile stress. Limit the tensile stress at 1000 Newton per mm square. Okay, so the limit is given here. So you need to limit the stress in this case to 100 Newton per mm square. That means this is the limiting stress, where it should be whatever the maximum stresses are should be lesser than or equal to the permitted one. So this is the maximum stress whatever we are encountering should be lesser than this value. So this stress is given in this problem. Okay, you are not required to find the stress, but you need to find what is the thickness, right? It's a simple enough problem, and also it's a combined load kind of thing. So you have this load of 5,000. We'll assume this is 5,000. Consider this as one more zero. Load, say F is 5,000 newtons. Let's assume that is 5,000 being applied at a point in the figure. So if you want to see a 3D of this, no, it will look something like this, I guess. More curved portion like this. There is curved over here, like this. I think you get the picture, right? It's a rectangular portion where this is the thickness. This h you need to find. So this here is given as 50 mm. From the front view, we can come to know this 50 mm, but this thickness is not there. The thickness is mentioned by h here. So this thickness of the plate is not known. So this is h is not known, and load is applied somewhere from this point, and it is likely to come out over here. This is the force, and this inner fiber, again, this is an eccentric load in condition problem, right? So it is being at this point here. This point, if you call it as let's say A is already there. Let's say B. Let's call it B. So B is here subjected to tension. Okay, because of this pulling action, you can see how it fails. It's the tearing will start from here. That is tensile, and this portion will be subjected to compression. Let's say C. So B is subjected to tension, and C is subjected to compression. Okay, so this we have seen how it happens, how it fails. You can just imagine how it fails. And one more thing to note here is always while testing of metals, we take tension test as the base or model for conducting the tests, because the materials usually they are stronger in compression and they are weaker in tension. Okay, this we have seen while defining the material properties in the first unit. Okay, since materials are weaker in tension, we will analyze only the tension part, because the weakest one will take into account. We are not to exceed this 100 newtons, right? So what we'll do, we'll consider only one case. Let's not find the compression, because usually in compression they are stronger, tension they are weaker. So we'll find the stress as for combined state only for tension case. Okay, got that? Right. So let's start off with this problem. Let me just copy this. Copy this entire thing here. Need a new diagram. Right. So that's the problem. Let's start off. Let's see what is given, the data. So data is, you need the load F which is 5,000 newtons, which is given. Then E is the eccentricity, is at 50 mm. So I'm writing E directly here. Why? Because you see here it's given as for the centroid itself. Okay, in the previous problem we had that a different cross section. So since the cross section was different, so it was difficult for us to find the eccentricity. So this is a cross section of this particular bar, and since the centroid is already given, which is half of this distance, that means it is a 25 or something. So already we know the eccentricity. No need to worry much, right? Then what do you need to find? So write down what you need to find. So since there are two conditions here, the tensile and compression, I told you compression it is stronger. So therefore we'll consider the tension part. Okay. So that means bending. Sorry, this is stress. So stress in tensile case. So let's say tensile case. So it is axial force by area plus. So I am writing plus is because it is tensile times MB C, right? MBC by I. Okay, so this is the governing equation to find the tensile stress, and also in turn we need to find the thickness H. So this is our ultimate goal, but this is our governing equation. And also given here is the limiting stress sigma, which is 100 Newton per mm squared. Okay, so this being our governing equation, let's start off. One by one we'll find. So force we know. Oh, but what is the area? For stress also we know, because limiting value is given. So it should not exceed this value. Stress we know, area we don't know, bending moment we don't know, C we don't know, and I also we don't know. So all these parameters are not. Let's find out one by one in this formula. So area first. So area is nothing but B into thickness, B into H, right? So B, I told you in the previous problem that take for the cross section wherever you have B parallel to. Okay, so B and H will pose a problem for you guys. So B here is nothing but this portion here, which is in the cross section parallel to it. Okay, that means that is H, not T. Okay. So if I were to draw the cross section here, no, how would it look like? I'll just show it to you. Put it here. This is the cross section. So you see it is following this pattern. Okay, like that. This is the cross section. So always try to embed the cross section inside the figure whenever you are solving the problem. Okay. So I told you this is the force being applied, and whatever dimension we have parallel to the force is called B. Okay. And this what we have is H. Okay, this H. That means H is known. So here is just trying to I don't think he's trying to confuse. This looks like B anyway. We'll make this B. What's it? We'll go back to question and check it out here. So it looks like H, but let's make this as B. Okay, because we should not get confused, because moment of inertia will change otherwise. Let's make all of this as B. Let's not assume that it is H. It is not H, it is B. Let's make this as B. Okay. Now, so what do we know here? B is not known, H is known. So let's do this. The area is B into H, which is 50. Okay. Now we know the area. Area is known, but only partially. Okay, that's our objective. And let's find bending moment. Okay, one by one. So bending moment MB is just force times eccentricity. So force is given 5000 into eccentricity is also given 50. So that means this is 5 5 is 25. 1 2 3 4 zeros. 10 power 4 Newton. Right. So that's our bending moment. So we have found bending moment. Next C is the distance from the neutral fiber. C means there is B by 2, not B by 2, H by 2 in this case. So C, this is distance from on the x-axis. Okay, that is 50 by 2. C is 50 by 2. That is 25 mm. Then C is found. Now the last thing is I. So I is moment of inertia. So I we know is B H cube by 12. Correct. So B H cube by 12. How did I get this? This is from the data handbook. I hope you remember from the data handbook. Right here. Okay, BH cube by 12. But note, this is not an actual show of the cross section. Okay, only you need to take for rectangular what is the moment of inertia. But you need to always refer to the figure here. You need to always refer to the figure where the load is applied. Parallel to that, whatever cross section we have, that is our load. Okay, that is our H. Here is where most of the time we'll make a mistake. B or H, which one to take. Okay, always note that whichever load is parallel to the dimension, okay, that is B. Okay, parallel line. It should be exactly parallel. So that is B always. Okay, in this way you will not go wrong. So that means this is B into 50 cube divided by 12. Okay, right. So now we have got the value of I also. So now since we have everything, let's just use this and find the values here. Value of B. So let's start substituting. So this is equal to force, which is 5,000 newtons by area was B into 50 plus bending moment 25 into 10 power 4, 25 into 10 power 4 divided by I is moment of inertia, B into 10 power 3 by 12. B into 10 power 3 by 12, denominator will become a numerator. So we'll put that into 12 again into this C. C is 25 into 25. There's one unknown here, and stress also we know. The stress is 100. It should not exceed 100 newtons per mm square. That's the stress. So with this, we will get what is the thickness B. So try calculate this and let me know the answer. So you're right with the answer. It is 7 mm. Thickness is 7 mm. B into 50 cube. That being said, and on your part, you need to just identify that it is the weaker member is always it is subjected to tension, whichever is tensile load, and we found the thickness. Right. So that's it. This problem is done. Let's move on to the next. Right. Okay. Check this out. So circular rod of diameter 50 mm is subjected to loads as shown in the figure. Determine the nature and magnitude of stress at critical points. Okay, check out what kind of loads are being applied on this. So critical points, I think just by seeing at this diagram, you can come to know where it fails. So there is a torque being applied, 1 kilonewton meter, which is the torque. I'll write it for you here. So MT is 1 kilonewton meter. 1 kilonewton meter is the torque. Also, you have a bending load here. So you see load being applied at the tip of this rod, the cylindrical rod. Diameter is given 50 mm. Let's note that. diameter 50 mm, then the length is 250 mm, and this load being applied here is how much? 3 kilonewton. No? It looks like 3. What can we say? Okay, we'll take it as 3 itself. So MB, not worry much. 3 kilonewton seems sufficient. 3 kilonewton of load, which is inducing the bending. You can see another diagram given just beside. This is inducing a bending load. Because of that, we'll get, oh, this is not MB, then it is just, this is not MB, this is just the force. So MB is bending moment, right? So that's not the bending moment. So it is force. Okay, force being applied in the radial direction of this rod here, and another force being axial. Let's say this is bending load, and this is axial. The axial load being applied here, it is 15 kilonewton, right? So in axial direction, this is trying to pull it away. This is trying to bend it, and this is trying to torque it, right? So that means, look at the stresses here. What all stresses are being applied in this diagram? Okay, so you have shear stress being acted here, bending stress, and axial stress. Okay, it is being pulled, bent, and also sheared. Okay, all these 3 loads. So this is a kind of a worst case scenario problem. All the 3 types of combined loading conditions are being applied to this, right? So let's see how we can find out the value. Okay, this is a bit of a lengthy problem, what we can say. So critical points are also mentioned somehow. Okay, check it out here. A. So because of the load, it may fail at A or it may fail at B. Okay, 2 points. Again, we don't know why, because torque is also being applied, because shear stress. We don't know whether it is being sheared or bent up in axial or torque because of the shear stress. We don't know exactly how it reacts. Okay. So there's a problem for us to solve. So let's start this. I'll take a screenshot of this first. Copy this. Let me start a new file for this. Save this. Right, so we have our problem here. Let's start off with the solution. So data, I think pretty clear. Nonetheless, I'll write once again. So data is, diameter is given 50 mm. Length is given, which is 250 mm. Then torque is given directly. We can write 1 kilonewton meter. So kilonewton meter, it's better for us to write it down as Newton mm. Okay, so 1 kilonewton, if you were to write as mm, no. So let's do that. Kilonewton and meter. So this means that how much is 1 kilonewton? 1 kilo means is 10 power 3. Again, you're converting that to mm. So 1 meter has again 1000 mm. So it is like this. This is in Newton mm. No, this is Newton mm. So kilo and mm. So just convert it. So that will be 1 into 10 power 6 Newton mm. So let's convert it to everything to a similar kind of units first. And what else is given? The bending force is given. So let's type an FB for bending. Then it is 3 kilonewtons. So let's say 3 into 10 power 3 newtons. It is 3000 newtons. Then axial force is 15 kilonewton. Then I'll write it in terms of newtons. And what else do we have? Yeah, that's it. Okay, so now what do we need to find? We need to find is let's go back to question. Nature and magnitude of stresses at critical points. So magnitude of stresses. So magnitude of stresses means, since here there are 3 different kinds of conditions. Here we have this bending axial stress, then we have bending stress, and also we have shear stress. So all these 3 things we have. So therefore, if you want to, if the component or the part is subjected to so many kinds of stress, the only way which you can determine is by principal stresses. Okay, principal stresses. That's what you need to find. That's what we need to find. Principal stresses, where you need to find sigma 1, sigma 2, and tau max. So this is the thing we need to find. Okay, that is sigma max, tau max, and sigma 1, sigma 2, principal stresses and shear stresses. Again, here this again breaks up into two portions. Why? Because you see the question in critical points. A, B both are critical points. So you need to find this for both cases. That is considering point 1, considering A, section A, and also considering B. So you need to find this at 2 points, because of the bending load, this will be converted into 2 portions, right? Okay. So before we start with this, let's find out the basic stresses, sigma A, B, and tau, the shear stress individually. So later on we'll club it using the principal stresses. So let's find solution. So axial force, simple. Let's say axial stress first. According to what we have written here, sigma A is just force by cross-sectional area. Force, axial force, axial force. So 15 kilonewton divided by cross-sectional area. Cross-sectional area is it's a circular cross-sectional area. Okay, so this is a circular cross-section area. Okay, so this part I'll write it over here. It's a circular cross-section area of diameter 50, right? So therefore, we'll write cross-sectional area here as pi by 4 into d square. D is 50 squared, right? So with this, we'll get what is the axial stress. Okay, try calculate that. And next, the bending stress, sigma B is bending stress. So bending stress is given by MB C by I, right? So that's the bending stress. So bending stress again is split as force into eccentricity or distance, force into distance into C by moment of inertia I. So these are very basic equations. These you can find from the data handbook also, but I suggest you try to learn this, because it will be helpful in various facets in your future. Okay, even in interviews and all those things will be very helpful. So I stress that you try to learn this bending moment basic formula. These are all common to basic formula, right? So again, let's expand this. So force, force here is bending force or bending load. So bending load was given as FB 3 kilonewton. So that's 3 into 10 power 3 into what is the distance? Distance is I think the entire length from the fixed point is 250 into 250 into what is C? C is just half, that's the centroid, that is the diameter by 2. Okay, I'll just elaborate this a little bit. T by 2 whole divided by I. What is moment of inertia? For moment of inertia, you can refer to the dead end. Here. So this is the circular cross section, and this is the moment of inertia. I hope you can see the moment of inertia I for a circular cross section is pi d power 4 by 64. You can extract the value from the data handbook here. From table 2.7, moment of inertia I is pi d power 4 by 64. Okay, this is pi d power 4 by 64. Okay, since we have 1d, 4 d's here and 1d here, we can eliminate one of the diameters here. So I'll take off 1d here and I'll make this d cube. So let me simplify this again. This sigma b is equal to, I can write this 3 into 10 power 3 into 250 divided by 3 into d cube, that is 50 cube. So this 2 comes down, so there will be into 2, and this 64 it goes up, 3 into 64, right? So you can calculate this and find what is the bending stress here. Now moving on, only one thing more is left to find, the shear stress here, tau. This also we have defined the basic equations. There is a shear stress. This is bending stress. Bending stress. And one more thing is shear stress. Shear stress given by tau. Tau here, the basic equation is mt c by j. Okay, this again taken from the data handbook itself, the basic equation, I think 2.6 or 2.8. But again, I hope you by heart this. So mt is directly given in the question, so no need to find another value for that. Mt is 1 into 10 power 6, right? And write that directly. So 1 into 10 power 6 into the c is 25, just like the previous problem, or 50 by 2, whatever. Okay, we'll write that. D by 2 whole divided by j. Now what is j? J, you see, is polar moment of inertia. How do you get j? Again, you will need to go back to data handbook. So it's giving you I, but in the previous table we saw that say, check it out, this polar moment of inertia somewhere here, I think. Oh yeah, here. So it's given polar section modulus. He has given. Is there any other table? No. So polar section modulus is a ratio of j by c. Okay, so we can condense this even further. So according to data handbook, let's condense this. So c by j by c is z. Is saying that is polar section modulus. So let's condense it to the same form. So this can be written as mt by j by c. This C goes to the denominator's denominator. It's C, and you can see J by C is nothing but Z here. So we'll make this as MT by Z. Okay. So once you make this, no, it will become simpler for us. So MT we know is 1 into 10 power 6 by Z for a circular cross section. This polar section modulus for a circular cross section is pi d cube by 16. Okay, you can write this value here, pi d cube by 16. Okay, for the section is pi d cube by 16. So that means is 1 into 10 power 6 into 16. So 16 comes to the numerator, divided by pi into t, that is 50 cube. This diameter we know already, right? 50 cube. So with this we can find what is the shear stress acting individually on that particular component, this particular component. So if you calculate it, just post in the group chat of the values. Which question is that? B 5. Let's discuss. Okay, so axial stress. Axial stress, come on, tell me the values. 15E3, 7.6, yeah, you're right, 7.6, 7.6, another decimal place before, Newton per mm squared, you're right, this is the axial stress. Then bending stress, say 3 into, you found out, okay, fine, good, you're right, this is 61.11 Newton per mm squared, and the shear stress tau is E6 into 16 over 5 times 50 cube. Okay, so shear stress, I think you get somewhere around 40 something, 40.74, I guess. Just correct me if I'm wrong. Squared. Yeah, you're right. So we have found the basic values of stresses individually. So axial, bending, and shear are all individually found out. We have individually found out, but this is not what we need. In the component, all these things are applied simultaneously. So if what happens if what is the end condition? That's what we are bothered. So that's where principal stresses come in. So this we'll solve in the next class.